This video continues optimizing the angle and the force required. And so we found the force through some force diagrams and quite a bit of calculus and a lot of mess. But we found the minimum force required, and it looks like this in yellow. And then from that, we've also found our, or from the derivative rather, we found that the optimum angle is going to be given by arctangent of k, whatever k happens to be. And so I'm going to come back and operate on this particular part right here. This is going to help me because I'm going to get rid of the angles in the force in the force equation. So I know that the tangent of theta is equal to k. Now this means that the tangent of theta is equal to k over 1. But generically, tangent of theta is equal to the opposite over the adjacent sides. So what I'm going to do is I'm going to build a second triangle here. And this is going to help me relate. That's all it's going to do. And so if I have the opposite here and the adjacent side here, then the opposite must be k, the adjacent must be 1, and so the hypotenuse is the square root of k squared plus 1 by Pythagorean's theorem. All right, and so now we want to find sines and cosines because that's what we're dealing with here. So the cosine of theta is given as the adjacent over the hypotenuse, which is 1 over the square root of k squared plus 1. K times sine of theta is equal to k times the sine is opposite, which is k, over the hypotenuse, which is square root of k squared plus 1, which means that this is k squared over square root of k squared plus 1. Combining these two, cosine theta plus k sine theta is equal to 1 over square root of k squared plus 1 plus k squared over k squared plus 1. When we add those together, we get k squared plus 1 on top over the square root of k squared plus 1. Now this is simply just, if we rewrite this slightly and say that this is the square root of that squared, now you divide the things in the roots and now you end up with the square root of k squared plus 1 as the answer. Now remember, this is all cosine, so cosine of theta plus sine, or k sine theta, is equal to the square root of k squared plus 1. Our force was equal to kw over cosine theta plus k sine theta, which means that our force is now equal to kw over the square root of k squared plus 1. So now we can calculate the force just by knowing the proportionality constant, and then we can, which is, by the way, called the frictional coefficient, or the coefficient of friction. And in this case, since it's not really moving yet, this would be the coefficient of static friction to get it moving. W is the weight. And so here's an example of kind of physics in action using calculus. All right, so now our question said, find the minimum force needed to slide the block and the corresponding value of theta. And so now, since I have force in terms of k, my theta, recall, was arctangent of k. Those are my two answers. Now, I would have accepted as well, if it were my class, I would have accepted this one right here, because you've already answered the question. That's the minimum amount of force necessary. Now that you have a value for the angle down here, it is complete. It might be nasty in its calculations, but it's complete. I just wanted to show you that you could carry it even further just by using a little bit of trig. And you could get it down into a much more simplified version that would be a lot easier to calculate. I love these problems. You really have got to dig into these types of problems and work your brain. It's a beautiful thing.